Let me welcome to the 32nd lecture of Drilling and Blasting Technology course. We are continuing our techniques of underground blasting from the last class, and you have seen in the last class we have discussed about the underground blast design, and you have been introduced with the different terminology of the underground blasting. You have seen in the underground blasting there are single free phase, and it is essentially required to create another free phase in that blasting, and the process where the another free phase is created, that is called cut area. And basically the underground blast design is mainly guided by designing the cut area. We have also discussed in the last class this designing of the blast for the cut area is basically divided into two parts. One is the wedge cut part and another is the burn cut part. So, in wedge cut two holes are drilled angling to each other of different degree, and this degree of angling depending on the rock mass condition. It may be lower for the hard rock condition and it may be increased for the soft rock condition, and other modifications of the wedge cut are also there, which are called fan cut, drag cut, which are half wedge cut, and pyramid cut is there, which is basically double wedge cut. So, basically wedge cut is having that angling drilling process, and it has been found this angling drilling is very difficult while the drilling is being carried out by a little bit not so much efficient driller. So, it is always wiser to go for the a parallel hole, and which can be very easily drilled by the driller. Another drawback has been found in the wedge cut, that the length of the drilling is basically dictated by the width of the opening. So, that is the main drawback of the wedge cut. So, we cannot go for a very longer drill, which essentially required to achieve a large production. So, to avoid these two cut, there are these two problems in wedge cut. There are other methods of designing this cut area, which is also discussed in the last class, that is called burn cut. So, this is up to designing of wedge cut we have covered in the last class, and we have understood the advantages disadvantages of the wedge cut in the last class, and our objective of learning objective of this class is remains same with the last class, that is to understand the objective of underground blasting, to design an underground blasting. And in designing process, in this case we are at this position, and in this class we will cover the designing of underground blasting using the burn cut. So, basically every class we start with the videography. Let us see this video, which is available in the YouTube also, that how the underground blasting is in general carried out. Obviously, visibility is little bit less. You can see this is the cut area, this is the tunnel area, and the surface connections you can see the nonels it is available in the surface. So, surface nonels are blasted, which are available on the free area. You will find out the blasting will be carried out little bit late, because the down the hole delay is there. So, now you can see the down the hole delay are blasted. So, basically the blasting is over now. Obviously, the visibility of the underground blasting is very poor, you cannot see the proper blasting carried out, but this is also giving you some good idea about the blasting. Last class we have also discussed that burn cut is basically a cut where cut area the parallel holes are drilled, keeping an empty large dia hole very close to the first hole to be blasted. So, basically the idea is that empty large dia hole, which are placed very close to the first blast hole, act as the free phase to that blast hole, so that free phase is considered say this is the total cut area, this is the cut area and this is the first blast hole, loaded blast hole, this is the empty hole. So, this loaded blast hole which is placed very close to the empty hole and this empty hole act as the free face to the loaded blast hole. So, basically this is the idea, so that after blasting of this one you can consider this portion is excavated. So, our free face is now like this and then the next hole which is blasted at this position will be blasted considering this is the free face and this portion of rock will be thrown towards this direction as this is the free face for this hole. So, this is the basic idea of this blasting. So, before next blasting this is the total free area available. So, like that way basically gradually we are increasing the free area or opening area, so that that can act as the free face to the next hole and by this way we reached the desired advance or desired pool after reaching this one. Probably by this time our free area is like this and if we are carrying out blasting then only this much of rock is being thrown towards this direction as this is the free area and this will give us the desired advance and by this way we can achieve the total cut area blasting. So, this is the main principle of the burn cut blasting and while we are designing the burn cut blasting, our first objective of this designing parameters are like this. We have to locate the cut area first, then we have to decide the empty hole diameter, blast hole diameter, then we have to compute the burden and spacing, length of the hole, explosive, delay element. Okay. So, this is basically our consideration and for this consideration we have to first design the cut location. The decision of cut location will remain same as we have discussed in the last class. Basically the cut area ideally is located in the central part. Unlike wedge cut, as in wedge cut we are having a wider cut area because the length of the hole depends on the width of the area, width of the opening. So, that is why we are having very wide cut area, but here the length of the hole does not depend on the width of the opening. So, that is why cut area may be small, the length of the hole depends on the empty hole dia. So, cut area may be small and that is why we are having option to place the cut area maybe at centrally or maybe in a little bit side part or maybe in side part, maybe in a upper part, maybe in a lower part. So, our option n number of options are available in this case and as cut area is having the largest concentration of the explosive, it is wiser to move the cut area in the repeated round. So, if in first round we are having cut area at this place, in next round we should have a cut area at this place, then we may have a cut area at this place in the next round, like that way we can change our cut area at different places. So, our next design consideration is the empty hole diameter. So, we have to first assume some empty hole diameter and based on that empty hole diameter we can have our first burden formula for the first hole. Say suppose this is our empty hole diameter, we have chosen dr is the empty hole diameter, then the first burden for the first hole is considered as this is as per Lange-Fors-Kihlstrom criteria. So, this first burden center to center, so this first burden distance is 1.5 dr for this hole. So, this is the first burden distance which is considered, and by this way we can have a square like this, where all the holes are placed at 1.5 dr distance. So, this is the first square. So, this is the first square, and then our considerations are like this. We have to increase this square in this form, and you can have this formula for these considerations of the square cut. So, this is basically 4 square cut, where it is considered if we are having 4 square like this, we can achieve the desired advancement, and the length of the hole, if we are considering this one, depends on the empty hole diameter with this formula as per the Lange-Fors-Kihlstrom guideline. So, this is important in the blast hole design for the cut area where 4 square cut is being practiced. So, as per this, the design criteria is very simple for a 4 square cut using burn cut, and that makes the burn cut very popular. However, one must remember that this design criteria is basically for the trial blast design, and you must consider this is a site specific constant. This is a site specific constant which may be changed depending on the rock mass condition. So, one must be very considerable for this using this 1.5 as a constant for the first burden value, and from the result observed in the trial blasting, these considerations may be changed. Basically, for this 1.5 acts good for the hard rock condition. In soft rock condition, if anyone is practicing burn cut, in general most of the cases soft rock formation we go for the wedge cut, but if we are trying to practice the burn cut, in those cases we must consider this 1.5 little bit higher than the this constant more than the 1.5 for the soft rock condition. So, this is in general the guideline for designing a burn cut for the cut area only. For next other holes, floor holes, wall holes, roof holes, and these are the stopping holes. These 3 are the stopping holes. For these cases, the formula may be like this, and these considerations will remain same for the wedge cut also. So, the formula for floor hole, wall hole, roof hole and the stopping holes upward, horizontal, downward in these 3 conditions remain same for the wedge cut and burn cut, because if this is the opening, this is the cut area, whether we are achieving the cut area either by burn cut or by wedge cut, it does not matter. The designing constraint for the holes remaining stopping holes and roof holes, wall holes and floor holes or lifter holes remain same. So, basically the designing of these roof holes, floor holes, wall holes and stopping holes does not depend on the whether we are designing our cut area either by burn cut or by wedge cut. So, design consideration for floor hole, wall hole, roof hole and stopping holes remain same for the wedge cut and burn cut, and these design considerations are like this. The burden considerations are like this. You can see these are the different considerations. The bottom charge lengths are given, the column charge lengths are given and stemming considerations are also given for all these conditions. Again, let me remind you that these are all for the trial blast design. Depending on the rock mass condition in your case, you must change these constants for your particular condition observing the trial blast design, a trial result of the trial blast design. The first burden, how you can achieve, this formula is given, that B in the previous slide you can see. You can see in the previous slide, this B is given. The value of this B, how you can achieve, is given by this formula, and this is Lange-Force-Kirchhoff formula. B is burden, S is spacing, F is the fixation factor considering the gravitational effect. This is the relative weight strength of the explosive with respect to ANFO, considering what explosive you are using. This is the linear charge concentration, and I think this C, actually this portion will come in the bottom. This portion will come in the bottom. This is basically C bar. This C bar is equal to C plus 0.05 for this burden, and C by this one using this, where C is the rock constant suggested by Lange-Force-Kirchhoff. In general, if it is not known to you, you can consider it is 0.4. So, this is the value you can consider, and using this you can get B. You can use this B value in the previous slides to achieve your different values, achieve the different values for the different components or different parameters. So, now let us see what will be the exact procedure of carrying out the blast design for an underground mining case or underground opening. Okay. So, in this case we should give some input parameter. Let us see what is the input parameter. We will discuss this for the burn cut. However, the procedure will remain same for the wedge cut, except for the cut area, where the area will be designed in different way other than the burn cut. So, this is the first, we need to have the different input parameters. Our first input parameter is the rock parameter, where the different rock parameter strength value etcetera will be required. Say as it is Lange-Force-Kirchhoff criteria, this values, rock characteristics values should be given here. Apart from that, we should have the opening parameters, say it may be tunnel, it may be underground opening. So, it may be rectangular, it may be circular, it may be D shaped, it may be horseshoe shaped, and with the different considerations we need to have the different parameter. For rectangular it is height width, circular it is diameter, D shaped then the width, height of arc, height of spring level, all these requirements are there, inclination is also there. These parameters must be there, otherwise in wedge cut how we will consider our drilling length. Then the explosive parameters is required, because explosive strength is very important, and drilling parameters is also required, because the diameters are very important. Our all design criteria depends on the diameter of drilling. So, these are basically the 4 input parameters, mainly rock parameter, opening parameter, explosive parameter, drilling parameter. All these are to be considered while we are designing an underground blasting. Then considering the input parameters, we have to design the output, and our first requirement, which is the main requirement, is that we have to design our cut hole first. So, in this case you just see the sequences. Here you can see the sequence is cut hole first. So, this is one, next we are designing lifter, next we are designing roof, next we are designing wall, and finally we are designing stopping. So, the basic criteria is that we have to see how much area is required to generate the cut. So, the cut area dimension is essentially required, this dimension is essentially required to achieve the desired pull and desired fragmentation. So, while the cut area requirement is fixed, now we know this is the cut area. We can place cut area at any place, but the amongst the total area, how much area is required for the cut, that is now known to us. Our next part is the lifter one. That means, for blasting the floor holes, how much area is required, but that means what will be the maximum burden we can consider for the last periphery holes, that has to be decided here. So, we can have the desired area to be blasted in the lifter holes. The next is the roof holes. So, we are fixing this part also, how much area is required for the roof holes, how much area is required for the roof holes. So, after fixing this area and this area, we have to fix the wall contour area also. So, this is the wall contour area remaining available for the wall. So, this is the wall contour area. So, our next process is to fix the wall contour area. After fixing this wall contour area, whatever remaining area is there, that has to be blasted with the stopping holes. So, our next idea is to create the opening in the stopping holes, and we have to find out what is the burden of the stopping holes, and knowing the burden of the stopping holes, we have to place the stopping holes. It may be like this, and in both the side. So, first we generate the holes for create the opening in the stopping area, then we basically place the other stopping holes to blast the remaining area. So, the stopping holes, the requirement of the stopping holes are decided at the last after fixing the cut area, then lifter and roof, wall and wall. The sequences may be changed for lifter and roof. You can decide the lifter first, roof first, lifter second also, or roof lifter first, roof second also, but after fixing roof and lifter, then only you can fix the wall contour holes. So, these are the requirements one must remember while they are designing the blasting for the underground openings. So, let us see how we can carry out. So, as we have already discussed, we decide the empty hole diameter, we have assumed some blast hole diameter to fix our concentrations, then using different formula we have received different cut lengths. So, these are the first square cut, these are the second square cut, these are the third square cut. So, these are different square cut are considered in the 4 square cut system. However, in this blasting I thought that 3 square cut was sufficient for this particular consideration. So, after fixing this one, the next lifter holes are decided. In lifter holes, if you see it already the cut area is fixed. So, the lifter holes are calculated first, and you can see the burdens of the lifter holes is fixed, then the roof holes are calculated and the burden of the roof hole is fixed now. So, burden for lifter hole and roof hole are fixed, these are not dependent. So, independently it can be fixed, and at this position our cut area, you can consider our cut area is now fixed, our lifter area is now fixed, our roof area is now fixed. So, these are the fixed conditions. Our next designing is for the wall contour. So, you can see in wall contour we have fixed this one, and considering this we have achieved, we can achieve the burden value of this for the wall contour holes sorry, this is for lifter holes, this is for roof holes, and we have achieved the burden of this one for the wall contour holes. So, this wall contour hole is now fixed. So, at this position we are in a process where this is the cut area, this is the roof area, this is the floor area, this is the wall area, which are already fixed. So, now we need to decide the stopping hole. So, let us consider the stopping holes now. So, in stopping hole, first we are considering the vertical rows. Vertical rows means this is the roof area, this is the floor area, this is the cut area, these are the wall contour holes, and vertical rows of holes means these are the holes which are considered the vertical. So, that this total area is considered as the excavated one, then the horizontal holes will be calculated. So, the vertical holes, the number of holes and number of rows, there it is 1 number of rows, that means this is not required as per this considerations, only 1 is available and 2 holes are there. So, you can consider 1 hole is there, this is not there, another hole is at this position may be sufficient. So, 2 holes are required, and only 1 row is required as per this consideration. So, using this only the total area may be considered as the excavated, so that the horizontal row may be placed. And in this case you can see this is the burden which is calculated. So, after decision of the vertical row, the horizontal row are calculated, where burden is found this one, row is found this one, number of holes are found this one, and this may be now designed like this. There may be a cut area, lifter area, roof area and wall area. So, basically as per our consideration, our cut area, as we are having only one vertical row, we can consider our cut area is like this. And these are the, sorry, there are 2 holes, these are the vertical holes for stopping holes, and there are only 1 horizontal rows of holes available in this condition. So, this is the design consideration, or you can see this is the design procedure one can follow while they are designing the blasting for underground, and this is the final consideration where all the burdens value you can see. This is the burden for lifter, this is roof, this is wall, this is vertical, this is horizontal stopping holes. And this is the summary you can calculate, and you can consider in this case this may be the cut area. So, this is the cut area, and this is basically showing the different delay. So, the delay, these are the first delay, then this is the second delay, then the third delay, then the fourth delay, then fifth delay, sixth delay, seventh delay, eighth delay, then 9th, 10th, 11th, 12th wall contour hole, then 13th, 14th, 15th, 16th, 17th, 18th, 19th, 20th, 21st. Okay. So, this may be the sequences. Obviously, you can blast this one and this one together, or maybe this one together on the same delay. So, n number of delays are required while you are practicing the underground blasting, because you can consider that significant number of delays, almost 7 to 8 delays are essentially required for only this cut area. But delay sequence must be proper, so that the proper expansion of the opening will be followed. So, that is essentially required in the underground blasting, and this is the main requirement of the underground blast designing. Delay sequence is very important. So, you can understand this is the effect of the joints. If the joint sets are parallel, obviously last class we are discussing about the pull, almost you will get good pull, because it is the very favorable condition, even if you can have more than 100% pull also in this case. In this case it is very risky, because as the joint set are vertical, in that case there may be higher roof overbreak, huge quantity of rock may fall from the roof area, and here joints are at an angle with the drive or tunnel axis, and it may be prone that the breakage will be with the joints, and an angled face may be observed, which is very difficult in the drilling considerations. So, these are very important while someone is carrying out underground blasting or designing some underground blasting, but for our requirement this is probably sufficient. However, you can go for more reading from these books. Again I am particularly referring Gustafson's books, Lange-Fors-Killstrom books, Jimenez book, SME handbooks. These are very important. Further readings are essentially can be carried out from this, and let us stop at this position. Next class we will discuss the result of the blasting. Thank you.